Good morning, good afternoon, and good evening, wherever you are. My name is Peng Wang from Nanjing University. My presentation is about ptychography single particle analysis for biological science. This is a schematic diagram of optical configuration for ptychography. Ptychography data was recorded in a scanning electron diffraction mode. Diffraction pattern were recorded on a Medipix 3 direct electron detector. The sample was vitrified using standard procedure and transferred into microscope and kept at liquid nitrogen temperature using a cryoholder. The face of the sample was reconstructed using ptychography iterative algorithm called EPI. The sample is vitrified here was rotavirus DLP with a diameter of 76.5 nanometer. This is a conventional defocused cryo TEM image at dose of 35 electron pounds on square. This is ptychography phase of the object at a dose of 23 electron pounds on square. In this enlarged image, the phase show a strong contrast from viral particles. Both capsid trimer of the viral protein 6 and the channel between them can be clearly seen. Most importantly, we are able to see the contrast from overall shape of the particle, which contain low spatial frequency. To confirm this, we further took FFT, which shows strong information transfer from intermediate spatial frequency extend down to 76 nanometer. To understand why ptychography phase contrast is stronger or better, we took a step back to see the contrast mechanism of defocused contrast TEM. This is a standard. This is a stained adenovirus particle to show you the size and the shape of the particle. In the imaging, people use unstained condition to preserve the native state of the sample. However, due to the weak scattering and radiation sensitivity of the biomaterial, the contrast at low dose is very weak, especially in the close focus condition. By looking at the CTF contrast transfer function at the close focal condition, it has zero crossing point at high spatial frequency and leave the lower frequency weakly transferred. To increase the contrast, we normally increase the defocus value to push the contrast contrast function back to the lower frequency, where we can see better. We can see the shell thickness of the virus better, but this causes a quick oscillation of the CTF at high frequency and scrambled high resolution information. Therefore, there is a trade-off between the resolution and the contrast in the defocus phase contrast TEM imaging. To enhance the overall the shape of the particle, ideally we need the transfer function to cover this bandwidth somewhere below 1/20 nanometer. But when we use defocus as large as minus 25.5 micrometer, the thorium shrunk to a low frequency and the particle become visible, but the first zero crossing moved to the 9.5 nanometer, beyond which the contrast for function oscillating dramatically. Therefore, it becomes really difficult to interpret high spatial information. And this is the ptychographic reconstruction phase of the object using 1.37 milliradian as a converging angle. It shows overall the shape of the particle with very high contrast. The co-shell structure with hexagonal shell matching the capsid coating and the triangular core corresponding to the internal genome. The power spectrum is continuous over the entire spatial frequency range and does not show the thorn ring like a conventional TEM. In order to understand why Tycho has better transfer at low frequency with 1 milliradian converging angle, we numerically calculate the phase contrast transfer function with the Poisson noise using a model of two-dimensional amorphous thin film. The calculation method you can see. You can refer to the SI in this paper. In comparison to TEM, we have three take-home messages. Firstly, using lower converging angle, for example 1 milliradian here, the contrast transfer function can cover a wide range of spatial frequency that is lower enough to reveal overall the shape of the various particles. Secondly, unlike TEM, the Tycho phase CTF does not have a zero crossing in the entire transfer range. That is consistent with the experimental observations, which means Tycho phase is not affected by the contrast reversal over the entire spatial frequency range recovered, and consequently, the resulting data can be interpreted directly and intuitively. Finally, we can change the converging angle to shift the bandwidth of the contrast transfer function from high frequency to lower spatial frequency, and this is a significant advantage for ptychography in that the CTF can be tuned to enhance the information transfer within a particular spatial frequency range for particular sample. To further demonstrate the tunable bandwidth of the ptychographic CTF, we reconstruct the faces of adenovirus at different converging angle of 1.7, 4.68 to 10 milliradian. And we use Fourier ring correlation to evaluate resolution with a half-bit threshold criteria. The result shows that the resolution increase as a converging angle increases. Recall that when we use converging angle 24 milliradian, we able to achieve atomic resolution with molybdensulfide sample. As we use a relatively large probe, 20 to 30 nanometer in diameter for experiment, this is possible to scan a large sample area with a small number of probe positions, further reducing the total dose. Together with this high contrast, ptychography can still clearly show the viral capsid shape and contrast of VP6 trimer at low dose as 5.7 electron per angstrom square. Another example shown here is HIV virus at very low dose. We still can observe the particle. Therefore, the ptychographic reconstruction is very low dose efficient, and can be applied to biological molecular imaging in cryo state at very low dose. Since a large number of faces of the specimen with high contrast can be obtained, we are able to apply the standard particle picking procedure that has been used for standard TEM-SPA single particle analysis. Multiple individual particle can be subsequently picked from the face and form into a stack of the particle face image. Based on about 200 particles, we are able to perform TEM-SPA with relying software and reconstruct this 3D map of the rotavirus. It is important to know that the procedure of contrast flipping is not needed, as the CTF for the ptychography has no zero crossings. So we able to in this 3D reconstruction, we able to directly observe the trimer layer here. I think it's really exciting time for electron ptychography, as it has shown many advantages. For example, light atom detection, low dose, and integrating with use and optical sectioning to tomography. And today we have talked about cryoimaging with SPA 3D reconstruction. So there are many opportunities for implementing this imaging technique. So here is the summary, and I think we have shown you first the cryo-electron ptychography with high contrast at low dose, as low as 5.7 electron pounds per square, and we have shown this method is suitable for biological imaging. This new approach provides tunable continuous wideband information transfer, including low spatial frequency that's accessible using conventional TEM phase imaging. We also have combined ptychography with single particle analysis for the first 3D reconstruction of the viral particles. We can foresee that ptycho SPA have potential applications to low symmetry or low molecule weight structure, or to bigger scale molecule architecture in the individual shells or multicellular organisms. And this work is a result of close collaboration among the people on this page. I would like to specially thank to the Angus Kirkland and his group from the APSIC and the Rosalind Franklin Institute for their great support and contribution to this project. Without them, it wouldn't be possible to accomplish this work. I would like to also thank Jing Dongsong from Chinese CDC, and Pei Junzhang and the David Stewart group from Oxford Biology for providing biological sample. And finally, I would like to thank Pete Nellis from Oxford, Xiaoqing Ban from UC Irvine for their strong contribution to this work. With that, I would like to thank you very much for your attention.